So yeah, the last time that we met, I think that I was here, we were discussing like just roasting different people's code. Not really roasting or doing a good job roasting, but anyway. And we looked at this like DrainableWorker type, data type, in the T3 code base, and we noticed that there were a bunch of like there was a lot of manual synchronization, like concurrency synchronization going on in this particular type. And we had just finished talking about STM. So it was like fresh on the mind. And it just seemed like this was a really good candidate for introducing STM in like an actual practical manner. So we talked about it on that stream, but we didn't implement it on the stream. But I promised that I would make a PR. And then in Discord DMs, Julius messaged me saying that he heard that I roasted some of his code, and he was asking me where his PR was. So then I was incentivized to make the PR. But anyway, if we go into here, and actually this will feature some improvements that Mike made to STM in general, which is cool. But yeah, the whole point of this DrainableWorker is to wrap a queue, like an unbounded queue, and also give you the ability to call this like drain effect that will only finish when both the queue is empty and the worker's idle. Like it's not processing. Like the items all the items have been processed. So we need a way to not only figure out when the queue is empty, which in theory, like in Effect v4, the queue does have a signal that you can listen to. Like when I think it's like await or queue.end or something like that. When you call queue.end, you can actually it'll block until the queue is empty. But that doesn't take into account whether like the processing of the item that you just took, the last item, for example, that you just took out of the queue is actually finished. So this type was basically enabling that pattern. You have the ability to call some method that blocks until the queue is both empty and the worker side that's processing items from the queue is idle. It's done processing all items.
Basically entering the state wherever you just enqueue something that will get executed immediately because the queue is empty and it's not processing anything else, right?
Yeah. Carefully code reviewing, not roasting. Exactly. Tasteful code review. So yeah, when we looked at this code, we noticed there was quite a bit of manual management of concurrency primitives. Like it was using deferreds to track when items were finished processing and whatnot, and it worked, but it was very vulnerable to like race conditions and different things that could go on. So we were talking about how we could use STM to make it better. And so we did that. So one thing you'll notice from if you've watched the office hours where we did discuss STM with Mike, you'll notice that like we're able to create transactional data types now without manually wrapping everything in effect.transaction. And that's because transactions are implicit now for methods that come from the effect library. So if we were to look at effect small, and we were to go into like packages, effect, source. Where are we? Transactional queue. Here we go. And if we look at const unbounded, you'll notice that this method itself, which should actually be an effect.fn, but it's not, is wrapped with effect.tx. And that's because Mike opened a PR a little while back. If we look for it, pull requests is closed and author is Mike. here. So basically, he renamed effect. I think with transaction or transact. Well, I don't know. He renamed it to effect. Yeah, he renamed it to just effect.tx to be shorter, and made it so that effect.tx will compose with parent transactions, so that like nested transactions will be able to compose nicely. So that enabled us to do the make sure that these methods resolved the requirement for a transaction internally. But then if you like wrap it with a parent transaction, you still get the transactional behavior that you're expecting. So that composition enabled this behavior, which is nice because now, like, if you want a transactional queue, you just call the like you normally would, and that behavior is enabled for you. But if you need to compose it with, like, if I wanted both the creation of my queue and the creation of this ref to be part of the same transaction, then I would just wrap both with a single effect.tx, and then they'd be part of the same transaction. So that's kind of cool. So anyway, we can take a look, run through this and see how much simpler it is. But do you mean atomic behavior, TX? Yeah, it's one and the same when we're talking about STM. Atomic, transaction, they're this. When we're talking in terms of STM, it's the same terminology. So anyway, the first thing we do is we actually create the queue. And before, this was a regular effect queue. Now it's a transactional queue. So we get transactional semantics on the queue. And we actually, I think maybe I can open up. Let me see if I can go back into Git history and like open up the previous version of this. Here. Browse files. Packages, shared source, DrainableWorker. So you can see there's quite a bit of like manual management of concurrency primitives going on here. We've got like this initial idle signal that we're using a deferred to track. We've got this like state that we need to keep track of. The creation of the queue, instead of being an acquire release, is done with a finalizer, which is fine, but it's like not really necessary. It can be done as one step. And then every time an item is processed, we call finish one, which basically updates the state and checks whether or not we need to like complete this deferred. And then every time an item is enqueued, we again update the state. We increment the number of outstanding items in the state, and essentially like it's quite a bit of manual management of all of this stuff. When we use STM, we get all of that like kind of for free, those semantics. So if we look at like this, and then we compare it to the STM implementation here, you can see like the STM implementation almost fits on one screen, which is for me, even zoomed in like amazing. This. It's very simple. So we've got a queue for our items that we're processing for the DrainableWorker. So we've got our queue, and then we have a transactional ref of outstanding items. And this basically is the counter that tells us how many items are still in flight, like how many items are still in the process of being computed. So this like process effect is still running for an item. So I'm going to skip down to adding items to the queue first. When we want to add an item to the queue, we just call enqueue here, and it will offer an element to the transactional queue. And you'll notice, again, we do not have to wrap these transactional operations with effect.tx by themselves. We can call them implicitly, but if we want all of this to be part of the same transaction, which in this case we do, then we need to wrap the whole thing with effect.tx. So that's what's going on here. We offer the element to the queue. So we make sure this happens. Then we also make sure that we update the number of outstanding items, the number of things that are in process. And then we wrap that with effect.tx. And you could do this update when you actually start processing an item if you want. but Julius chose to do it this way. It's kind of the semantics of when to do this are kind of up to the implementer based on the behavior that he needs. So anyways, hopefully this makes sense. And queuing both offers the element to the queue and updates the transactional ref that tracks the number of outstanding items in a single transaction. So this will always be like a transactional or an atomic operation. And if either of these do not succeed, the
entire thing.
they'll be retried. The whole transaction will be retried. Okay. Maybe now we can take a look at the background fiber that we spin up to pull items out of the queue and process them. So for this like background fiber, we want to first take a single element off the queue, right? So transactional queue. And again, this is a transactional take. So we're not wrapping any of these with a outer transaction. We want this to be a transactional take. In case there's an interruption or something like that, we don't want the whole thing to like hang. So we take an element off the queue, then we tap or flat map, whatever, it doesn't really matter in this case. We get said element, which we're calling A here. We call process, which is the function that comes in from the outside. And then with an effect.ensuring, we make sure that no matter what happens here, whether it succeeds, fails, or is interrupted, we always update the outstanding transactional ref by decrementing the number of items in process. This way, once process is finished with whatever exit state it finishes with, we always decrement the counter. So we can make sure that when we do call drain, we have an accurate count that we're draining with. And then we just repeat this forever. So we're constantly always trying to take items off the queue and process them. So we're doing that in a forever loop, or the effect version of a forever loop. Since this is not like it's not a busy loop, it will yield in between iterations. And then we fork that into the background. So this becomes a fiber that's attached to the lifetime of which is attached to this scope. So if this scope is ever closed, this fiber would be interrupted. So this is the background fiber. So when we enqueue an item, it'll be taken off the queue by this background fiber and processed. And this is a very common pattern in the effect ecosystem for producer consumer type services, where you're producing elements into a service and then you have some work that you want running in the background to consume said items. And then the last piece of this, which is interesting, is the drain operation. So this constructor, make DrainableWorker, exposes both the enqueue and the drain operations. The fiber is just a implementation detail that's happening in the background. But drain is important because this is the signal that lets us know if we've actually finished processing all items in the queue. So here we get the number of outstanding items. So if you recall, outstanding is the ref tracking how many things we still have in process, in flight requests, I guess you could think of them as. And then we check if the number of outstanding items is greater than 0. And if it is, then we know we need to keep looping the STM. We need to retry the whole transaction. And to do that in STM, you call effect.tx retry. So this, when STM is executing, when it sees a transactional retry, it will retry the entire transaction, which in this case, since we're wrapping this whole operation with effect.tx, these two operations here become part of the transaction. So when we call tx retry, it will, the next time this runs, it will try to get the outstanding ref, get the count, check if it's greater than 0. If it is greater than 0, it'll retry again. But when we finally get to 0, then we call void, which lets everything continue. And that basically is the simplified version of this DrainableWorker data type, all powered by effect's implementation of STM. Which again, like if you look at the previous implementation, it's much more verbose and error prone to do this manually, as opposed to doing this as part of an STM transaction.
I mean, now it is something like 20 line of codes, right? Yeah, if you look from 30 to 60, and before it was about like at least 3 times of what we had before. And it had a lot of edge cases where we could eventually, like, interruption could break something, and whereas instead now STM gives us that guarantees of perfectly aligning and having like a synchronization primitive that allows us to ensure that we add to the queue and we increment, and we do that either all or nothing transaction beauty.
I think Julius did edit this after the fact, but in my implementation, I think I had, hang on. In the implementation that I contributed, I had to fix a bunch of things because I was upgrading the v4 version. Here we go. View file. I think in my implementation, yeah, in my implementation, NQ was a simple offer. And I chose to do the increment of the outstanding ref as part of like taking an item from the queue. But maybe for whatever reason,
I would say that probably one reason could be that if you do that, it means that if you check immediately after you have enqueued, if you like call enqueue and then call immediately the drain, sorry, it will hit immediately a case where probably you would not have yet have time for the other fiber to take the item and start setting the pending. So potentially you could have, I think, a condition where you can like push some items. But ideally, yeah, no, sorry, never mind. Because the queue should, when you offer, the queue should be waken up. Yeah.
Well, that, and also this is part of a transaction. So if take fails, we should just end up retrying. Yeah. So I think both implementations have their merits. Again, Julius, I think, let's see why he did this. Yeah, I don't know. Changes STM concurrency semantics for Drain by relying on a single counter updated. I don't think this changed anything because I also only had a single counter. But
who knows?
Whatever. Yeah, I don't know. There maybe there was a good reason for maybe it was. I know that he changed drain semantics here, where my drain was checking both whether the queue was empty and if there was anything in flight. But I think that that behavior was modified by him. But I do, like, personally, I think that this is incorrect right here. I think this is incorrect. Julius, if you're watching, I think this is incorrect. I wouldn't update the outstanding counter because, like, it depends on the semantics of what outstanding means in this case. Like, if outstanding means are there elements in the queue, then sure, this is fine. But and maybe that's why maybe he wanted to simplify this piece of code to not also have to check if the queue is empty. I guess that's what like the PR was saying. But I don't know. I think that like semantically, to me, it makes more sense to increment the number of in-flight requests when you actually take an element out and start processing it. But that's okay. I think both have their merits, and it certainly simplifies the implementation of Drain. It's just that then outstanding items are kind of overloaded with like the concept of whether the queue is empty or not. But